Hey everyone, we're going to continue our discussion on Bode plots and how we can use it for stability criterion. So some information on Bode plots, a little bit we've already discussed, but we're going to just enhance that discussion. So the gain K can be described using this AR or amplitude ratio, as well as the phase. And we're going to use this discussion to discuss multiple pieces of this. So when we think about the gain, the influence that the gain has on the AR is that when the frequency is 0, so right at the start, my gain is actually equal to the absolute value of my amplitude ratio. So they become equal, and thus the log 10 of one is equal to log 10 of the other. But when we think about the contribution to the Bode plot, when our gain is positive, our phase starts at 0 degrees. But when the gain is negative, the phase starts at minus 180. Definitely important to remember. Our poles, which are just in the denominator, allow us, just like we discussed last time, to describe our AR, where the left-hand pole or the right hand, so the left-hand plane and right-hand plane of our poles, they allow for a decrease in the slope by 1, where the numerator zeros for the AR increase the slope by 1. So this is the slope of that log of AR specifically, and that we're going up by 1 for every 0 and down by the poles. You could think of that in terms of the fact that we have here, let's write it up here, Tz of s plus 1 over Tp of s plus 1, where these are our zeros, and these are our poles. So we're talking about, for the AR, we're increasing the slope by 1 for everything up here. We're decreasing the slope by 1 for everything down there. So not too bad to remember that if it's a numerator, it's increasing, and if it's a denominator, it's decreasing. The effect of our phase is that we, for the left-hand plane poles, we're going to add a minus 90. For the right-hand plane poles, we're going to add 90 degrees. And then for every 0 in the left-hand plane, we're going to add 90, right-hand plane, the opposite. So they're just the inverse of each other for that. The integration term, 1 over s, for our AR, it's directly equal to 1 over w. So we're just substituting the s with the w there. And we could think of that because of the substitution normally of s equals I times j. Same thing, actually. My apologies. W times j. I and j are the same thing. Where now we're thinking about, okay, well, that is plus 0 for my real term, and this is my actual imaginary term, so it becomes 1 over w, substituted directly, where then we can see that the log 10 of AR is now equal to log 10 of minus w, or negative log 10 of w. And we could see that for the phase, this is going to add a minus 90 for all of the w specifically. In the time delay effective term for our AR, we're just taking the absolute of G here, which is essentially the absolute of AR. And in that case, we're looking for the gain directly. That is going to be ultimately plugged in for S as JW. That gets us into 1 by the Euler formula. And for the phase expression, this is minus W times theta now, and based on the radians to degrees principle, as W goes to infinity, my phase will also go to negative infinity. So more or less, these are just some elements to remember and to think about as we discuss and consider Bode plots and their characteristics. So when would we use this? Why is this critical? Let's think about Bode stability criterion. So a new element here. All of these are the same. I've just moved the dV down when I usually put it above. This, totally new. An open loop system. It is not connected, but we can connect it. So we can move this into a connected state, but for right now, it is not connected. Totally wild, but stick with me. This could be real. We might stop the loop, and we might need to see that this goes from an open loop into a closed loop system. But we can consider the open loop characteristics to define the closed loop characteristics that will then exist. So 3 pieces of information to consider. First, the dV. That is one of our 2 inputs. So when we think about the dV, we want to then introduce, okay, if there's no dV, then there's only our set point existing in the system. And if it's currently in an open loop system, then it's going to have to consider all the things that would be in the loop when we close it. So when we consider that, our open loop itself, that's currently then moving out here, will include all of our transfer functions that are passing through, just as before for the closed loop system. Therefore, we'll have our controller transfer function, our process, and our sensor. The AR of that open loop is going to be based on the magnitudes of each multiplied, as we discussed previously, and we can add those phases to get the general open loop phase for all of the system. We're still going to be using a set point input of our sinusoidal because now we're discussing the possibility that that is having a modification, in that we're looking into sinusoidal planes. The second piece is we want to consider then a lag between our CVM here and our set point here. So naturally we want to get error. Our goal is to get an error function where error of S is equal to my set point of S minus my CVM of S. That means it's the center output for my transfer function from CV. So that's the error that we're looking for here. But we might have a lag as we go from an open to a closed state, and where when one of them is normally going to be like this, if there's a lag by 180 degrees, that means that now the opposite one looks like this. So that would look like if you added them together, essentially, that if you directly did an addition, they'd cancel each other out. But if you subtracted them, you'd ultimately just get something that looks like this. So what can we do with that information? Well, we can consider that in the AR for the open loop system then. We are considering a lag that then describes a minus 180 phase, and that directly, based on our previous rules, will be allowing for an AR open loop of 1 directly. So if we close the loop and now set our set point equal to 0 here, we would get the same time, at the same time point, we get the same error as before. What does that mean? Well, if the set point is set to 0 now, then the error function is directly equal to negative CVM of S. But in reality, this is talking about the negative of the negative, because we've set based on a lag of 180, which is that. So minus 180 degrees. Therefore, the error function prior will now equal the error function after, based on that rule. I'm writing the way. The third thing to consider is the AROL being greater than 1, equal to 1, or less than 1. So if it's greater than 1, we're going to go off into an unstable phase. This ends up being in a right-hand plane, so it is unstable, goes off, and it's just completely oscillatory on forever. If it's equal to 1, it's just a perfect sinusoidal oscillatory curve, kind of like here, which is totally fine. But if it's less than 1, we're going to actually become stable, and as time goes to infinity, we're going to actually localize in and converge to 1 value, which is great. So a big rule of thumb at the end of the day is once we close the loop based on that information, the closed loop system will then only be stable if AROL is less than 1. And this is because we're trying to see what's happening stability-wise when the loop is open before we actually close it. So if it's already stable when it's open, then that means it's definitely going to be stable when we close it. And we're going to look for something called the critical frequency, or WC, which really just happens to be what happens as it goes on to forever, like t equals infinity, but we're looking specifically for then the minus 180 point. When my phase equals minus 180, that becomes my critical frequency, and that's the value we're looking for, which usually happens as we go on to infinity. So all these together, we're just taking our standard approach of our expression where we have gain, and we have, like, say, my transfer function is k e to the minus s theta over ts plus 1, our standard first order function with time delay approximation. How does this influence our system if our set point input is now a sinusoidal function? We're plotting it out with Bode plots, and we can see these relationships pretty discreetly. So pretty cool stuff. I'm going to erase the board just to discuss a little bit about phase margins and gain margins, and that will really close out our discussion on Bode plots. So to finish out our discussion on Bode plots, we're going to discuss something called the gain margin and the phase margin. So the gain margin is the value of our gain that only impacts our AR open loop, so the amplitude ratio in the open loop, in the overall transfer function of our open loop, GLOL, which is the multiplication of GC by GV by GP by GM. That's all inside the open loop, but it does not impact the phase of our open loop. So that means that there is no phase value contribution of the gain at all, making that 0 degrees. WC, in that way, this critical frequency that we find, will not impact that. We won't be changing it for any value of the gain that we choose. So we can look for a maximal gain that we can add multiplicatively that can influence our system and change out mostly just this discussion. So let's create this new expression term. Whenever we're at the critical frequency, we want to find what that AR open loop value is, and that is 1 over the gain margin. So the gain margin itself is 1 over AR open loop at that frequency, but we can find that graphically. So if we look at the phase, we're looking for then when this crosses minus 180, then we move up to here, and that AROL value yields the gain margin. We want the gain margin itself to be greater than 1 for the system to be stable, because we want AR open loop to be less than 1. And because those are inversely proportional, we can see that to be true. So a factor by which the gain can be multiplied before reaching an unstable system is really all we're searching for here. We can also use this information then to find the ultimate gain of the system. So we're multiplying now the gain of the controller, KC, by GM, or dividing KC over that AR open loop value, and that gives the ultimate gain for our entire system possible. And so the KC itself would be nice for like a proportional controller, but for any PID control, we can use this effectively the same. In addition, when we look at this plot here, notice there's something here called the phase margin. So we have that WG value, this crossover frequency that happens between the 0 and 180 at the minus 90 value. And that could be seen here happening exactly when AR open loop equals 1. So when that is true, as we discussed previously, we see the influence on our phase, and we know that to be true, that this is happening to become the phase of the open loop at that crossover frequency. So we see the influence it has on both plots, but what we're really looking for now is the phase margin. So the actual difference here, which is related to the time delay in the system. The real question about this is how much time delay can be added into the loop before we actually become an unstable system. So we're trying to find the difference essentially between where that value actually is in minus 180. And so that's what we're searching for. We can use this then to find out delta T max, or the actual time delay, because it is based off of time. And so it is the time itself multiplied by 1 over time, or frequency, and that then yields out the phase margin, so the degree or radian based change that's existing here for the system. And so we can actually look directly at this and say, okay, well, this difference is effectively the phase margin, because phase margin then is this minus this, which is what we actually see here. But phase margin can also be explained using WG value itself multiplied by the delta T, and then use the radian to degree conversion effectively from there. And so really all we're looking at here is stability. We're looking at an open loop system that could become closed, and defining the closed loop system by the open loop stability criteria, because that's a little more challenging. And that makes sense, because if we open and close a loop and it's sinusoidal, we need to see what the change would be at any point in time later, and how that affects the constantly dynamic system. So this really does introduce true dynamics in our system. It's a great way for us to think about these more complicated critical control theory problems, and works well as we now move into the more complex side of the course, like feedback control, feed forward control, and cascade control. So hope you had a great time, and I will see you soon.